In this video, I'm going to talk about the creation of A-class fillets. We're also going to look at how to create corner fillets and deal with the so-called Y fillet, where two fillets come together and wash out to nothing. We're going to start by discussing some of the design, engineering and technical requirements of fillets and explaining the terminology. There are a number of functions that we can use to create fillets: round, surface fillet, symmetric fillet, freeform blend and profile blend. We'll discuss their uses and merits. There's also a type of fillet which I call an offset fillet, which is useful when it comes to dealing with corners. They can make life a lot easier. Corner fillets can be created using the ball corner and corner blend tools. But if you want the ultimate in control, which we always do when we're creating A-class surfaces, then manually creating corners is the best way. There are many times where fillets wash out to nothing. We'll look at constructing a two-fillet washout condition, or Y fillet. The principles that we'll use to construct the Y fillet can be used in many other areas. From a design perspective, fillets are needed to smooth out sharp edges. Their exact size and shape is always very important to the designer. From an engineering viewpoint, the minimum radius is a particularly important factor, both in terms of pedestrian or occupant safety and feasibility issues such as metal forming limitations. The other requirement is for fillets to meet certain technical quality standards. As always for A-class surfaces, we want simplicity in terms of minimum degree and number of spans, and we want the edges of the fillets to be as clean as possible. The fillet edges need to be aligned to the block surfaces, and the CVs need to be as tidy and as well spaced as possible as well. Let's talk about the terminology. Edges of fillets are known as fillet rails, or edges of course. Fillets are referred to as being G1, G2 or G3, which refers to the continuity of the edges to the block surfaces. The crosswise shape is usually called the section. If we create fillets using any of the fillet menus, then the U parameter will be along the length of the fillet. It's worth knowing this if you want to display the section curvature. You should always select curvature U in this case. If the fillet is circular, then the section curvature will of course be constant. Circular fillets are not used very often in A-class surfacing. The reason being is that they look very hard at the edges. Sometimes you'll need G1 fillets with run-in. Run-in, or lead-in, is where the curvature starts low at the edges, increasing to the minimum radius at roughly the midpoint of the section. This will make the fillet edges look softer. But for the ultimate in soft edges, we would use G2 or G3 fillets. The simplest type of fillet is one where the section is circular. The round function can be used to create circular fillets. It is powerful because we can specify different radii on each edge, and the corners are created automatically. But it should never be used for A-class work. Firstly, circular section fillets are rarely used on A-class models, and secondly, the fillets that round creates are poor quality. They're okay for CAS or visualization, but not good for A-class. You can see that when we analyze the corner radii using the principal maximum display, the corners are not 100% accurate. Round creates a fillet of degree 3 only, which means that the curvature cannot be accurate, certainly for larger fillets. Round gives us no control over the degree or spans or the end conditions. The continuity of the edges may not even achieve G0, let alone G1, so for A-class surfacing, using round is out of the question. However, it sometimes can be used in A-class work for packaging checks. In this example, we have a surface that needs to clear a packaging object by 10 mm. If we take the package model and offset all of the surfaces by this amount, and then use round with a radius of 10 mm, then we'll have a package envelope. We can use this to assess whether we have enough clearance between the surface and the package. The benefit of round for this application is that all of the edges can be done in one go, including the corners. A far more useful function, and one I use for most of my fillets, is surface fillet. This has a very high level of control with all sorts of section shapes possible. The function automatically creates the rails based on the radius or chord values. Continuity can be anything from G0 for chamfers up to G3, and the end conditions can be controlled using the flow control settings. The simplest shape that we can create with surface fillet is a degree 1 flat chamfer. For A-class work we would usually add crown to this. Flat surfaces are generally avoided unless the geometry is very small, in which case crown is less noticeable. The amount of crown is a design decision. Usually it will be quite subtle, just enough to counteract the illusion that the flat surface is bowed the wrong way. We've already discussed how circular fillets are seldom used in A-class. This is mainly because they have visually hard edges. However, there are times when they might be needed. It may be that your company standards will allow or they require circular arc fillets when the fillet radius is less than a certain value, maybe 3 or 5 mil. Sometimes there is not enough space to have G2 fillets, and so circular fillets can be the answer. In this case we would specify G1 circular if we want the most accurate circular section shape. By default the cross-section degree is 5, which gives a very accurate curvature result. One thing to be aware of with circular fillets is that if you run them over each other, then alignment is going to be more difficult to achieve than with G2 or G3 fillets. The G1 tangent option also creates a nearly circular fillet when the form factor is 1. Adjusting the form factor will alter the shape by pushing or pulling the CVs towards the centre of the section. We can therefore use form factor to add run-in to the fillet. G2 curvature means that the fillet rails are aligned in curvature to the block surfaces. This is the shape that I use the most. It's fairly simple as the degree is only 5, but it gives nice soft looking edges. If you want the edges to be even softer looking, then use G3 curvature. G3 means that the slope of curvature at the edges is matched to that of the block surfaces, and by default the cross-section degree is 7. In general I only use these for very large fillets where I need a very soft effect. With smaller G3 fillets I've sometimes found that the designer will say that they look too soft, in which case G2 is a better option. One advantage of G2 fillets over G3 is that the corners may only need to be degree 5 by 5, and they're therefore simple to build manually. Of course, the choice of G2 versus G3 may be dictated by your company standards. G2 curvature with arc is a recent addition. The idea is to have a fillet with an arc-based centre section with G2 continuity at the edges. Obviously this is far more complex than a simple G2 degree 5 fillet, and the corners are going to be much more difficult to construct. Bias allows the user to shift the balance to one edge or the other. This is not something that I've ever found a use for. If I did, I'd probably achieve a similar result by moving the CV hulls instead. The lead option gives us a G1 degree 3 fillet. The knee ratio is similar to the form factor in that it allows us to slide the CV hulls in and out, and therefore affects the amount of lead in. The result is very similar to G1 tangent, but with a lower degree. So we've looked at lots of options that control the cross-section shape, but which ones should we use? Obviously if we need a chamfer, then we'd use the chamfer option, but always with some crown on for A-class work. We rarely want completely flat surfaces. In general, we always want to use G2 or G3 fillets for A-class work as they give a softer look than G1. I think it's a good idea for all users in a team to use the same form factors. This makes working on someone else's model so much easier and gives a consistency to the models. Personally, I nearly always use G2 fillets with a form factor of 1. Being the default, it's easy to remember. There are arguments for using form factors other than 1, which is fine, but it's one more thing that we have to make sure we get right every time. I might use G3 if the fillet's very large, where it's more of a blend than a fillet, for instance to define the corners of a bumper. Otherwise it's always G2. We've already said that G1 fillets are generally avoided because they give a very hard looking edge, as you can see here. In fact, they make the block surfaces look hollow. If you look at most mass-produced industrial products, you'll see these types of fillets. I've even seen them in train carriages. In the car industry, though, they're generally not acceptable. The only time that G1 fillets may be allowed is if they're very small, say less than 5 mm, or if there's limited space. You should check with your company's standards to see what is acceptable or required. If we compare G1, G2 and G3 fillets of a similar section shape, then you'll find that the higher the continuity level, the larger the caudal distance has to be. In other words, G1 fillets take up less room than G2 or G3. So if space is at a premium, then G1 fillets may be necessary. In this example, we want a minimum radius of 2 mm, but there isn't enough room for a G2 curvature fillet with that minimum radius value. A G1 circular fillet of radius 2 is one option, but of course this will have very hard looking edges. If we want a slightly softer looking result, then we could choose lead instead, which allows us to have some lead in at the edges. If we want a G1 fillet with lead in, there's actually two options, either G1 tangent or lead. We can get very similar results with both, so I'd always choose lead because it's got a lower degree. When it comes to checking the minimum radius, there are two options. You can either use the control panel and curvature, or you can use the principal maximum option with the minimum radius specified. Here it's 50 mm. Principal maximum refers to the curvature, not the radius. Hence why we use principal maximum to find the minimum radius. When it comes to the fillet edges or rails, these are controlled indirectly in surface fillet via the radius or chord values. In the other fillet functions, such as symmetric fillet, freeform blend and profile blend, the user can input one or both rails directly. Let's first look at the radius option in surface fillet with G1 circular. In this case, the radius value obviously specifies the radius of the fillet. The fillet edges will then be automatically positioned to achieve this radius. If we change the section type to something else, such as G2 curvature arc, then you'll see that the edges don't move. In other words, they're always determined by the rail positions of G1 circular. Also notice that the radius label has now been replaced by tangent offset. As the angle between the block surfaces varies, then radius will result in a variable caudal distance. In other words, the distance between the fillet rails. Usually we don't want this with A-class work. Usually we want a constant caudal distance, and so we would use the chord option instead. This controls the distance between the fillet rails. It's the minimum radius value that then varies. If we need to check the caudal distance, we would use the curve-to-curve deviation menu. The ends of the fillet are determined by the flow control options. There are 4 options. Default gives a fillet which completely lies inside the block surfaces. Extend gives the result that you might expect. Edge align results in an end which flows tangentially into the block edges. Connect just connects the end with a straight edge. In general, default and edge align are the most useful. If you use any option other than default, you may find that the CVs towards the fillet ends do not behave well, or that the number of spans increases a lot. If so, then it's often better to use default. Then extend the fillet outside the fillet function, and finally trim or trim convert the fillet back as necessary. There's one thing to be aware of if you use edge align, or if you trim convert a fillet at an oblique angle. If you measure the minimum radius with the control panel, you're then measuring the radii at an angle across the fillet. So the value will not be the same as if you use the default fillet, where the function is measuring along the true radius direction. The principal maximum display doesn't care if the ends are oblique or not. it will always display the true minimum radius. Sometimes the surface fillet, and also the other fillet options, may give you a very high number of spans to achieve the edge continuity that you want. In that case, you need to use explicit and set the number of spans lower and the degree higher if necessary. The default degree is 5, but there's no reason why it can't be higher. Making it higher will reduce the number of spans that you need. You can adjust the degree and spans to whatever you think should be a suitable value, even if the continuity is no longer achieved. Then come out of the function, delete the curves on surface, and align with project onto the block surfaces. Often this gives a much simpler result. Now we come on to symmetric fillet. With the surface fillet, the fillet rails were controlled indirectly via the radius or chord values. With symmetric fillet, we can directly specify one of the edges as either a curve on surface or a block surface edge. The second edge is created automatically to give a balanced or natural fillet. In other words, the second edge is built at an equal distance from the theoretical intersect. Often I start with a surface fillet. If one of the edges has a slight wobble in it, then I may create a new cleaner curve on surface on this side and then use symmetric fillet to hopefully create a better result. Here we have an example of using symmetric fillet with a projected curve on surface, and this enables us to adjust the fillet very easily. In this situation, the block surfaces are at different angles. The fillets all have the same chord value. This means that the lower edges of the fillets are at different heights relative to the top surface. If the top fillets need to flow around the corner, then the bottom edge of the corner fillet will be S-shaped. To avoid this, we could use what I call an offset fillet. In other words, we offset the top surface to create curves on surface for the fillet edges and the corner fillet. Then we would use symmetric fillet to give a totally consistent set of fillets. The corner surface is then very neat. This may not be appropriate in all these types of situations because it does result in varying radii on the top fillets. The freeform and profile blend functions seem to be very popular with cast modelers. I'm not going to cover these in detail here. They can be useful for A-glass work, but I think more so for large blends rather than fillets. If you do feel the need to use them, then be careful that the fillets are either balanced, in other words the distance between the theoretical intersect and each edge is more or less the same. If you need a J-shaped fillet, or blend, then be careful about the placing of the CVs. If it's a G2 blend, then there should be 3 well-placed CVs on each side of the theoretical intersect. They should not cross over, that's for sure. To summarise, in general, we mainly want to use surface fillet with G2 caudal and a consistent form factor, which for simplicity should be 1. G1 circular fillets are not used very often for A-class work because their edges look very hard and they make the block surfaces look hollow. So we should only use them if our company standards allow or require them. They're usually only allowed if the radius is very small or if space is an issue. G3 fillets are usually only needed when the fillet is very large or if your company standards dictate this. They'll need more space than a G2 fillet and can sometimes appear too soft. We always need to respect any minimum radius requirements. Now we're going to look at how we can achieve the best quality fillets. In other words, how we can get the most accurate but simplest results. We're going to look at the factors that affect this by looking at the surface fillet again. Here we have a degree 2, 3-span surface intersecting another simple surface. I've deliberately chosen a low degree multi-span surface to illustrate a point. We would not usually want a degree 2 multi-span surface for A-glass work because the continuity at the knot lines will only be G1, 1 less than the degree. If we try and create a fillet between these two surfaces with explicit off, then this is what happens. The function really struggles, especially in the area of the knots. We get a very high number of spans. By default, the fillet is degree 5 along its length. This means that the fillet will be G4 continuous at its knots, whereas at the block surface knot lines we only have G1 continuity. This is why the fillet is struggling so much in these areas. If we use multiple surfaces with Bezier, we get fewer spans, but there's still a problem around the block surface knots. Let's go back to a single fillet and increase the degree of the block surface. This of course changes the shape slightly, but it also increases the continuity at the knots. Now the fillet has less of a problem in these areas, and so there are fewer spans. Switching on Bezier again, we get an even better result, but it's still not the best. One thing that's not great is that the ends of the Bezier surfaces don't line up with the knot lines of the main block, which is what you might expect or want. But we can make this happen if we convert the main blocks to Bezier using Surface Edit NURBS. If we switch on Explicit, we can increase the degree in order to minimize the number of Bezier fillets. To take this even further, we can fillet each pair of surfaces separately. This means that we can minimize the degree of the fillets for each section. Here we have multiple surfaces, a mix of Bezier and NURBS. There are 4 in total. The initial result with Explicit off has an excessive number of spans. With multiple on, but not Bezier, we get slightly fewer spans. But to get the simplest, most accurate results, we can split the NURBS into Bezier as we did before, then fillet between each pair of Bezier surfaces using Explicit to increase the degree and reduce the number of spans. We may well have to use a line afterwards in some areas, which does mean more work of course, but it does give us the cleanest result. We're now going to look at a method for creating corner fillets. The same principles can be used to create any corner, whether we have G1, G2 or G3 fillets. But in this case we've got 3 G2 fillets of roughly equal size coming together. For A-class work, a triangular corner surface would not be acceptable, so we have to create a 4-sided corner surface. We first of all need to decide which of the block surfaces should be our base surface. In this case, because all the fillets are similar, we can choose any one of the block surfaces as the base. So I'm going to choose the top one here. If our corner was triangular, then this would be one point of the triangle. But in order to make it a 4-sided surface, I've opened up this edge here. The corner surface needs to be aligned in curvature on all edges. We'll start off with degree 5 by 5, but sometimes we have to increase it in order to achieve G2 continuity on all of the edges. When we get to the point of trimming back the fillets, it's best, for A-class work at least, to leave the fillets as trimmed surfaces rather than trim converted. The reason for this is twofold. Firstly, if we needed to analyze how the fillet was built, or to build another one with the same parameters, then we can use the metadata. We can't do this if the fillet has been trim converted. Secondly, if we want to analyze the curvature across the fillet, then it's better to do this on the trimmed surface if the curvature sections are now true, i.e. they're at 90 degrees across the fillet, and therefore they give the correct minimum radius values. With an obliquely trim converted surface, the radius values are not the ones that we're after. For cast work, it's just easier to use the trim converted fillets only. We're going to make the corner surface by firstly creating the hole that the corner sits in. We'll then build a surface using square. If we try to do this with the trimmed fillets, then we get a very bad result. It's always better to do this with the trim converted fillets. So what we need to do for A-class work is to keep the trimmed surfaces in the final model, but we'll use a trim converted copy as a construction surface that we can use to actually build the corner. Now let's go through the process of building the corner. There are many ways in which this can be done, but this method gives consistent results with perfectly aligned CVs. In this example we're building a G2 fillet, but the same principles can be used whether it's G1 or G3. Firstly, we need to create curves on all of the curve on surface using duplicate curve with no rebuild. Now we'll isolate these curves. Let's trim all the lower curves to each other. With the top two curves, we need a curved fillet between them. On the lower edge, we could use blend curve, but now I prefer to use an edit point curve. We need to then align this in G2 with history on. With all the geometry visible again, we need to adjust the CVs on this curve to line up with the holes of the fillet. If you look at the relationship of the fillet holes to the fillet edges, though, you can see that we need to adjust the curved CVs slightly to one side of the fillet holes. What we're creating manually here is ideally the same as the trim converted edge that we're going to create. In other words, the curve should lie exactly on the fillet surface. And we can check this with the curve to surface deviation function and adjust the CVs a little bit more if necessary to get as close as possible. Now we're going to trim the lower fillet to the curve. We'll also make a trim converted copy of this for construction purposes. This will be used for actually building the corner surface and then thrown away, leaving only the trimmed fillet in our final model. Trim convert is only ever an approximation of a trimmed surface, unless the trimming is along an isopalm. So we need to check the edge continuity against the trimmed version and increase the degree of the trim converted surface if necessary. The left and right hand fillets now need to be trimmed. To do this, we're going to create planar cutting surfaces which are tangential to the edge curves. Firstly, we'll extend the edge curves with linear and no merge. This creates a line which is tangent to the end of the curve. Then we'll connect the end of this line to the end of the top curve with another straight line. To create the planar surface, we can use the rail function. This surface will be used to trim the fillet. But to make sure that the planar surface is completely intersecting the fillet, we need to first scale it. But before that, we need to center the pivot. Now we can trim the fillet and create a construction copy using trim convert as we did for the first fillet. As before, it's important to check the edge continuity against the trimmed version. If it's not G2, then we'll need to increase the degree. We repeat this process on the other fillet, and again we'll check the edge continuity between the trimmed surface and the trim converted copy. Now we've got a hole where our corner surface will sit. When you're building the corner surface, it's essential that you pick the trim converted construction edges, not the trimmed surfaces. Templating the trimmed surface will help get them out of the way for now. To create the surface, we'll use square with the continuity that we want and collinearity specified on each edge where it's appropriate. To get the CVs tidier, you can adjust the blend sliders, although I don't normally bother, as we're going to planarize them later anyway. It's very unlikely that we'll get continuity straight away. Usually we have to align afterwards. We're going to try and get alignment first before we start tidying up the CVs. When we're aligning into the trim converted construction surfaces, we need to have edge and position influence of 1 on. Normally I try and align the lower edges first and then the top edge. We can try G2 on all 3 fillet edges, but you'll usually find that this pulls the surface away from the other edges, so you may have to drop down to G1. At the bottom of the Align menu there is an option to specify a different continuity check type, and it's worth seeing what happens if we set this to G2. You might be surprised that even though you're only aligning in G1, that you've actually achieved G2 in some cases. Sometimes you'll find that one edge is not quite aligned. In this case, we might have to move the CVs manually. If we put a comb on using the information window, then we'll be able to see more clearly what's happening as we move the CVs. On the top edge, it's usually best to delete the curve on surface and then align using project normal and position influence of 0 so that the CVs don't move too much. You can try G2, but again we might have to go for G1 and then check the result for G2. Our final step is to tidy up the CVs. Now, since we trim converted the left and right edges of the surface with planar surfaces, the internal CVs should also be planar. To make sure this is the case, we'll use Planarize Hull, but we have to set up the correct view first. We're going to do this for each hull by defining a plane using 3 points based on the CVs. The first 2 points are going to define the lower tangent condition, and the third point is from a CV on the top edge. We'll pick the CVs using Control, which can be a little tricky sometimes. You may find that sometimes it picks the surface rather than the CV. It seems to work best if we pick away from the CVs rather than trying to pick exactly on them. Now that we've picked the 3 points, we can set this plane as the current construction plane. And if we go into the left view, we'll see that the 3 CVs we've picked all lie on a straight line. So we'll use Planarize Hull to tidy these up. Here we need to set Single, View-Based and Closest Boundary. What Closest Boundary does is make sure that the CVs slide down the hull in the direction of the nearest edge, rather than being projected normal to the plane. This means that the G1 and G2 continuity at the nearest edge shouldn't change, or if it does, the change will be very small and one that we can fix easily by moving CVs around. Having planarized one of the hulls, we're simply going to repeat this process on all of the hulls. In other words, defining and setting a 3-point plane, going to the left view, and then planarizing the hull in this view. Any small errors in the edge continuity that we get, we can fix by moving CVs around. To complete the corner, we'll delete or hide the construction surfaces, bring back our trimmed fillets, and trim out the block surfaces. We'll also need to check that our corner is aligned with the trimmed fillets. In this example, we're going to look at an area where 2 fillets merge into one and wash out to nothing, the so-called Y fillet. If one of the fillets was larger than the other, you could run one over the other, but here we have very similar sized fillets coming together. The technique I'm going to show you here is a get-out-of-jail-free card in many situations where there's no obvious patch plan. The principles of this technique can be applied in other areas as well, where multiple surfaces come together. This is what our final surface layout will look like. The end surface resolves the transition between the 2 fillets and the main block. The trick is in building this surface correctly. So the first step is to build a single surface which approximates the whole area. We'll then split this up so that we can align it into the fillets accurately. First of all, we're going to create a 4-sided hole. 2 of the edges are obvious. We'll need to trim back the large blend to make the 3rd edge. But the 4th edge is the most difficult because it consists of 2 fillet ends. So let's trim the large blend first. We'll do this by creating a curve from the corner of the small fillet to the opposite edge. We'll make this degree 5, just like the large blend surface, and then we'll align this in G2 to the fillet edge. We can adjust the CVs until they line up with the surface hulls like we did before on the corner fillet, and create the shape that we want. Now we're going to trim convert with duplicate. We need to make sure that the deviation between the original and the trim converted version is not too much. It should be less than 0.001. If not, then we'll increase the degree. The edge will never be 100% the same as the curve, but if we align the surface to the block surface with edge align on, then we can make sure that the edge is aligned properly. We only need to use G1. G2 might change the surface too much. You can see that the accuracy of the surface is still good. Now this is a trim converted surface, so we're going to use that for construction, but we really want to keep the original surface in our final model and then throw this construction surface away. So here we'll trim the original and then template it to keep it out of the way for the moment. Now we need to create the fourth edge of our hole. What we'll do here is to build a single curve that approximates the two fillet ends. So firstly we'll do a planar cut on the two fillets using a line in a view. The first end of the line needs to be at the intersect of the fillets. The second edge we're going to line up with the isopalms of the large blend. The reason for this is that our final washout surfaces will then align more easily with the blend later on. If we extend this line, we can then use it to trim convert our fillets in a view. With the top fillet we want to keep the original, so we're going to use this as a reference for the shape of the corner surface later on. With the lower fillet we don't need to keep the original surface. In fact at the moment it's not aligned anyway. So now that we've trim converted it, we'll align it into the large blend. Now we're ready to create the fourth edge curve. We could use a blend curve, or if you prefer, a degree 5 edit point curve, which will then align in G2 to the fillet edges. To make it easier to see, I'm going to turn off all of the surface CVs. Notice that when I put this curve in, I'm picking on the edges away from the ends. If you pick on the ends, then you'll find that the tangents are pointing the wrong way. Now I'm going to line in G2 with history on, so that we can drag the endpoints all the way to the ends. It's then a question of adjusting the CVs until we get a good fit to the fillets. The CV pattern looks really strange at this point, but it will all work out in the end. We should try and make each set of 3 end CVs reasonably equally spaced. So now we have our 4 edges, and we can put in a square surface with G2 on 3 of the edges. Whether we get G2 or not really doesn't matter. It's more important that the degree is low at this stage. Once we have our square, we can align the edges as we need to. You can see that the top fillet is poking through a little. We need to adjust our surface to get a reasonable approximation here. We also need to look at the tangency to the fillets. We're never going to get alignment, of course, with one surface. That's only going to happen once we split the surfaces up. We can use sections, X or Z, to give us a better idea of how close we are to the long fillet. It's only near the top edge that, of course, it's going to be close to this fillet. We might use a line with history and then adjust the CVs using PMOD to start with. We'll then do some fine-tuning using individual CVs. Non-proportional viewing always helps to assess these sort of patterns of CVs. The CVs will look a little odd to start with because they overlap, but you'll soon get used to seeing them this way. And we're just looking for good, clean patterns. If we can get the tangency to the fillets below 2 degrees or so, then we're doing well. And the highlights should start to look consistent with the other surfaces at this stage. The final stage is to split up the surfaces and align them. We need to divide the surface into 3. Where we divide them is a matter of judgment. We don't want the first divide to be too close to the fillet ends, otherwise there's a risk of wobbly surfaces when we come to align them. For now I'm just going to detach the surface at some point, keep the original, and then template this to get it out of the way. Then we can detach the left hand side so that we now have 2 connection surfaces. As we've created these surfaces all from one, then all of the internal edges will be perfectly aligned. It's only the left hand edges of the connection surfaces that actually need aligning. The CVs of the connection surfaces won't line up exactly with the fillet ends, not surprisingly, but they should be reasonably close. Now we can align all of the edges. In order to keep the CVs tidy, we should create a plane from a view roughly normal to the surfaces in this area. Then we can constrain the CV movements to the Z direction. First of all, we're going to align the left-hand ends to the fillets, but only in G0, with position influence of 1 so that the CVs line up exactly, and we'll also need to have blend on. We need to blend all the way to the other end so that the hulls are linear in this view. It does mean that we lose continuity at the other end, but we can get that back later. And also it's really important that history is off. The next step is to try and align in G2 with vector Z on. Sometimes we use only G1 alignment, but then check whether G2 has been achieved. And again, we might be surprised that we've already got G2 even though we're only aligning in G1. And if necessary, we might have to increase the degree, of course. If it's not completely aligned, then we can fix small issues by manually moving CVs. And if we put combs on the diagnostics, this can help us understand the effect of moving each CV. And to start with, we're going to just move the CVs only in the Z direction, but you might find that it's better to slide them or move them in the normal direction as well. Above all, what we want is neat CVs. And looking along the ends of the hulls is often a good way of assessing them in 3D. The quality of the final highlights will depend very much on how accurate the large corner surface was, and you might find that you have to revisit the original surface a few times to get the very best results. The common edge we may not achieve G2 on in all cases, but as long as the highlights look okay, then this is usually not a problem. We can also assess this by looking at the curvature across this edge.